Hello, everybody. Welcome back to our discussion in dynamics. Today we'll talk about the final thing that belongs to this chapter, momentum of particles. And this last thing that we're going to talk about is angular momentum of particles, which, by the way, is not on midterm 2. Yes, we just gonna do it, but we just gonna do it anyway. And we just gonna do one example, and then after that one example, we will talk about midterm 2 review. Midterm 2 content is work energy and momentum of particles, and more details on that later today. Okay. And as usually, I just would like to wish you good luck on Monday. I will keep my fingers crossed for you, for sure. Without further ado, let's dive straight into our discussion. Example number 1. As usually, please read and understand the problem statement. Okay, so what do we have in here? We have a table. Yes, we have a table, and we have a particle moving on that table. Yes, the trajectory of the particle is that spiral. I hope you can see. Okay, and the thing that causes that spiral is that chord. Yes, there is another constraint attached to our particle, that chord, and somebody is pulling that chord down with velocity 0.2 meters per second. Aha, little typo here. Yes, I should put 0.2 here, 0.2. Yes. Okay, our particle has mass 2 kilograms. Our initial radius is 0.5 meters, radius of curvature, of course, and our initial angular velocity is 1 radians per second. They ask us to find what is the tension in the chord and what is the angular velocity of the particle when radius of curvature is 0.25 meters. Questions about the problem statement? Solution then. So since they ask us for tension in the chord, I don't know, I would go first for free body diagram just to see the forces acting on our body. So I would go for FBD at arbitrary instant. And also KD, of course. So let's draw that table. Actually, we should not draw that table, yes, because on that free body diagram there should be only a body, yes. So actually, I should draw here just one dot here. Okay, this is our free body diagram. However, let's introduce that table with a dashed line. Okay, let's pretend that the table is still there. Okay. So I should do exactly the same in here. So this is top view. But let's also maybe look at the table from the side. Okay, I also want to have a side view. So in here we will have something like that. And here is that hole in the table. Okay. So this is side view. So what forces act on our system? I believe that there is mg acting on our system. Oops. And in here it will be acting this way. of course. There should be reaction force, yes? N. And there is one more force acting on our system. It's of course that tension in the rope, yes? So let's also draw that rope. That rope is here. So that will be tension in the rope. Okay, I don't think that there are any other forces acting on our system. So now kinetic diagram. I believe that trajectory is a spiral, right? Yeah. So what coordinate system you would like to go for, guys? We can choose from Cartesian, r theta, and nt, right? That was the third one. So this is our trajectory. Any suggestion? Which one is the more comfortable? Second one, yes. R theta. Zach is right. So we're gonna go for this one. Okay, so let me introduce that coordinate system here. So that would be UR. This will be U theta. And this will be K. Okay, so once we have our coordinate system, we can draw our inertia forces. So this is MAR. This will be MA theta, and this will be MAZ. Okay, we are done with our kinetic diagram. So what was the next step in our solution? Equations of motion, right? So now EOM. Since they ask us to find T, I would go for sum of forces along the R direction. So I think that sum of forces along this direction is only minus T. And this is equal to MAR. That's all. Yeah, there are no other forces acting along that direction. Okay. So what's the next step? I think that our next step should be expressing these guys in some useful way. So AR, if I remember correctly, was R double dot minus R theta dot square, and A theta was 2R dot theta dot plus this. Okay, and now we should plug this guy in here. Yeah, this is exactly what we're doing. However, before plugging in, let's maybe simplify that equation. So if I scroll up the board, you guys can see that actually I can maybe copy this. So they told us that velocity is constant, yeah? Velocity of that cable. So what is this value, guys? R dot. It will be negative 0.2 meters per second. And this is constant. So that means that our R double dot will be 0. So that means that this is 0. Okay, so now we can write minus t is equal to minus m r theta dot squared. And this is equal to t. Let's get rid of these minuses. T is equal to m r theta squared. Okay. How many unknowns do we have? I think we don't know t, and I think we do not know this value, unfortunately. So we have one equation and two unknowns. So far, so good. Are you with me, guys? Any questions, by the way? Okay, so we need one more equation, yes? To be honest, we can find it. We can find that second equation if we go for this equation. F theta, and this is, let's say, sum of forces in theta direction with this direction as positive. However, there are no forces acting along this direction, yes? Along this direction, there are no forces. So we can write here 0, and this is equal to m a theta. So that means m cannot be 0. M cannot be 0, so that means that a theta has to be 0. Okay, and that means that I must plug this thing in here right now. So that means that 2r dot theta dot plus r theta double dot is 0. So if we can actually find theta dot via if we integrate this equation, if we integrate this equation. But we're not going to do it. We could do it and we could solve it. However, topic of today is what? Is integrating equations? No. Topic of today is angular momentum. So we're gonna take equivalent procedure, okay? Instead of integrating this equation, we will go for angular momentum, okay? And we will find theta dot that way. Let's look at angular momentum. Angular momentum. And find theta dot that way. Okay. So, let's look at angular momentum about point B, okay? About point B. And point B is the center of the table. Let me scroll up the board, okay? This is point B. I think even they showed us it in the picture, yes. This is B, here. So point B will be here. B and B. Okay, so what I would like to do, I would like to write down angular momentum equation. So it will be H initial about B plus integral from T0 to T final of momentum about B dt, and this is equal to H final about B. However, we just care about Z component of that vector, okay? So let's actually put everything in the parentheses, and let's care only about Z component. So this is by definition, but this is by definition. How I know that I should go for, because some of you are thinking why I know that I should go for this equation. This is definition of angular momentum. Look at the lecture notes, okay? And now I would like to prove that this guy is zero, actually. I would like to prove that this guy is zero. And I will just show you guys that angular momentum is preserved. So let's put question mark in here because we don't know it yet, but we are going to prove it. So what forces act on our system? We have, I believe, tension in the cable. We have mg. And we have also normal force, yes? So each of these three forces can generate momentum acting on the body. But these guys are equal to one another, yes? mg is equal to minus n vector-wise, so that means that mg is equal to n. So that means that momentum generated by mg will be cancelled out with momentum generated by n. Yeah, and you guys know that because if we do sum of forces along the z direction, we will end up with, let's say this is positive direction, we will end up with minus mg plus n, and this is equal to maz. But due to the table, this has to be zero. So that means that n is equal to mg. Just to be clear, these forces do not generate moment in that particular example, okay? But even if they did, that momentum generated by this force and the other force will cancel out each other, okay? So now let's see, we ended up with only one force, yes? So let's see what is mb of force T, okay? So I think that the definition of that is R times T. And let's express everything in this coordinate system. UR, U theta, and K. So I need some help. Maybe some of you would like to help me. Could you please express this vector in UR, U theta, and K? Anybody? Trevor, you are always active. Yeah. Wait a second. Yeah. Anybody want to help me? What shall I write here, here, and here? Josh? Perfect. Yes. R00. Exactly. Yeah, because R is equal to RUR. Yeah. In other words, if I zoom in here, you guys can clearly see that our R is aligned with UR, yes? And now I would like to express T as well in that coordinate system. So if I scroll up the board and I look at this drawing, you guys can clearly see that T will have components minus T00. Minus T00. Okay, let's do our determinant. So that this will be UR U theta K R00 minus T00. Okay, and this is equal to 0, 0, and 0. Perfect. So our momentum coming from T is 0. Okay, but we, in particular, we care only about Z component. So you guys can clearly see that this guy can be eliminated. So we can clearly see that momentum is preserved about point B. Momentum preserved. Sorry, angular momentum. Angular momentum preserved about point B. Okay, so I'm gonna steal this equation. No, so we can write HB initial Z is equal to HB final, but Z component only. Okay. So now our goal is to find angular momentum. So H by definition is R times MV. Yeah. Before I move forward, any questions? Yeah. AJ?
Does it not matter that T is like going through the hole, so it wouldn't be like T in the direction or
Yeah.
or or
So I will answer. I do not understand your question first of all. Yeah. So this T is going through B. Do you see it? This is point B. T is going through that point. Such forces do not generate momentum at all. Okay. And these guys are aligned with Z. They also would not cause any momentum about Z. Okay. But even if they do, they will cancel. That moment will cancel out. Yeah. That would be my answer. Is it okay? Yeah. So yeah, I don't know. Thank you. Yeah. Anyway, any other question? Okay. So now let's find this thing. So you guys told me that this is R00, and the other vector will be M. If I remember correctly, R dot R theta dot 0. So let's do this determinant. So we'll have R theta and K 0, 0, 0 mr dot mr theta dot 0. Let's solve this determinant and let's see what will happen. So we will have 0 here, we will have 0 here, and we will not have 0 here. We will have mr squared theta dot plus 0. Okay. So this is our momentum, angular momentum of the particle about point B. But we care only about Z component. So H of Z is equal to mr squared theta dot. Alrighty. So now I'm just gonna plug this thing in here. I'm just gonna plug this thing in here. And let's see what will happen. So initially we had mr0 squared theta 0 dot is equal to mr final squared theta final dot. M's cancel out. And I think that we would like to find theta final, yes? So theta final dot is equal to, oh, come on. Is equal to r0 squared, r final squared, theta 0 dot. Plug in values. If I remember correctly, this is 0.5 squared, 0.25 squared. I forgot what theta 0 was. I must scroll up the board, okay? 1. Times 1. If you grab your calculator, you will obtain that this is 4 radians per second. So probably you don't have to grab your calculator at all. Yeah, and that's it. Yeah, this is theta final is equal to 4 radians per second. This is our answer to part B. Yeah, so we could obtain it via integrating the previous equation, but we just did it via looking at angular momentum. Okay, we solved part B before we solved part A. So let me just solve part A as well. So I'm just gonna plug this theta dot final into this equation we left earlier. So now let's find the tension in the cable. So all of a sudden this is known. And our tension will be, what was the mass? I also forgot, sorry, I must scroll up the board. Mass was 2 kilograms. 2 times, I changed the notation, yes, during it. So it should be not R theta, but it should be R final, yes, theta final, yeah. But you figured that out, guys. So R final was 0.25 and theta final was 4 squared. Grab your calculators and obtain that T is equal to 8 newtons. This is our tension in the cable when R is 0.25 meters. Answer to part A. And that's it. Questions? Mike is yours.
When you were proving that the moment was going to be zero, did you know that from intuition from looking at the problem, or did you have to solve it first?
From intuition.
Okay.
That it's gonna be zero?
Yeah.
No, I didn't know. I just went for it. Yes, yeah. Plus I am so-called instructor. Yes, yeah. I mean, I am like a grotesque one probably. Yes, but yeah. So I personally I don't think much. So I usually go for brute force methods. I will go for this one right away. But I got orders and I must follow orders. Today's topic is angular momentum. That's why we go for angular momentum. Okay, yeah. Anybody else? Yeah. Okay, that was not that bad, yeah. And this is not on the midterm too, by the way. Angular momentum is not on the midterm too. Okay, guys. So plan for the rest of the discussion is review for midterm 2. Do you want to see it? Or, you know? Okay, so I prepared something. However, I don't want to do it actually. Because, do you know why? Because I watched lecture yesterday, and Professor Sani did a great job there with his review, in my opinion. So I'm just afraid that and it's so good, I'm afraid that anything I say can only spoil it. Okay, no? Yeah. So make sure, for those of you who didn't attend yesterday's lecture, and even if you attended, watch the last, there's a video recording of the lecture. Yeah, watch the last part of the lecture. I think, in my opinion, it was a very good review. Yeah. Did you come here with questions? By the way, do you have already some questions? No? Okay, so you can think about questions while I'm gonna try to review the material, okay? Okay. So, what is the content of review of material of midterm 2? What is the content of midterm 2? Work energy of particles. And if I scroll down the board, there will be also something in blue. Aha, yes, and momentum of particles. Okay, so let us start from beginning. So, if you run into problem and you decide to solve it with work energy, just follow our recipe, just follow our solution steps. So what I would do I usually write down this expression, T1 plus V1 plus U12 non-conservative equals to T2 plus V2. Second step, finding these 5 guys correctly, of course. Third step, plugging everything back into our original equation. And the fourth step, solving the equation. That's all. Easy points? Kind of, yeah. Yeah, I have nothing else to add. So that was like what we started with. Then we talk about internal forces. Yes, that when there's an internal force in the system, it don't do any work if objects do not move relatively to one another. For example, tension in the cord. Tension in the cord does not do any work in the system. However, if there is a sliding in the system, so if two bodies move relatively to one another, then such friction between them will do some work. Yes, we did like 1 or 2 problems. I think even 2. We did like 2 problems. Yes, of that kind. Yeah, that's it when it comes to work energy method. I have nothing else to add. Then when you're asked to do something with power and efficiency, I have no recipe for that. I usually just write down this equation and this equation for efficiency and power respectively, and I try to figure stuff out. This is my recipe. Okay, questions so far about work energy? Yeah. You're Daniel. Yeah. Yeah. You mean this one? Yeah. Yes. That was easy question. Thank you. Yeah.
So just like a mental sanity check here, conservative forces would be like MGH springs, and then non-conservative forces would be like friction, normal forces, applied forces, things like that.
Yes. That's also, yes, that's my answer. Look at your notes. We did it a couple of weeks ago, yes? Examples of conservative forces. Exactly what you said. Gravity, linear spring, cubic spring. And non-conservative forces are friction, applied force, very rarely aerodynamic drag. And you're Jaden. Yes? Okay. Yeah, this is very, very, very rare case in this course. So just focus on these 2 probably. And you said normal force, yes?
Yeah.
But we also showed that normal force does not do any work,
Right.
yeah, because it's always perpendicular to the displacement. Yes. So in this course, 99% of the time, reaction forces don't do any work. Yeah. Okay. Good question. Yeah. Okay. Any other question about work energy? Okay, you can ask it later if you want. No worries. So now let's talk about momentum of particles. So if I see such problem, I actually feel, so if I see such problem with that can be solved with momentum of with momentum, linear momentum, I usually start with momentum diagram. Yeah, I think it's not required. I'm not sure, but you can just draw that momentum diagram just to have it, yeah. And then maybe if you do like a little typo, it's a good argument for regrading your work, yeah. So I usually do it. You don't have to probably. So what I show on the momentum diagram, I show initial momentum of particle, yeah. Then here I show final momentum of particle, and in here I show impulse acting on particle. Okay. And once I have this momentum diagram or diagrams, I just write down momentum equations along the x direction, y direction, or any direction I want. Yes, we do you remember there were problems where we were writing these equations along the t direction, for example. Yes, some other direction. Yeah, so in here I just show initial momentum in the x direction. In here I show final momentum in the x direction, and in here I show impulse acting on the along the x direction. Analogically in here, but everything along the y direction. Yeah, that's all I want to say. Maybe one thing. Sometimes we don't go for these two equations. Yes. Do you remember sometimes in our solutions? Sometimes we just needed only one equation. Yes, because something interesting was happening only along one direction. Yes, and we were just skipping the other direction because it would not give us anything. Yeah. Yeah, I have nothing else to add. How I'm doing so far? It's a good review so far. Yes. Okay. Thank you. Any questions about linear momentum of particles? Okay. And so then what was the next sub-chapter? It was direct impact. So direct impact means that all the velocities are aligned with line of impact. Okay, all the velocities lay along that line. So how to solve this problem? But then maybe before the solution, I will just tell you what is on this picture. Okay, so we have two bodies. Yes, we have little guy and big guy here. Yes, little particle and big particle. And in pre-impact, little guy is chasing the big particle. Yes, and after the impact, big particle should have larger velocity than the little particle. Yes, otherwise it would not make too much sense physically. So in that case, during direct impacts, momentum is preserved always. Momentum is preserved. So if I scroll up the board, just this is zero. This is zero during impact. And also this is zero. That's why in this equation we have initial momentum that is equal to final momentum. That's it. And usually in here we do not know these values. Yes, we usually do not know these values. This one and this one. So we have two unknowns and one equation. So we need one more equation. Yes, one more equation, and that one equation is coefficient of restitution that is presented here. Once you have these two equations and two unknowns, you know exactly what happens post-impact. Special case of direct impact is impact against the wall. Yeah, special case of this type of impact is impact against the wall. In here we have only one body, so that's why we are just going to go for one of these two equations above. So I'm just going to use, in here I usually use simplified version of coefficient of restitution. Yeah, because this equation is exactly this equation. However, these guys are zero. This is zero, and this is zero. Yeah, so we just simplified this equation. And this is how we know what is velocity final. Okay. That's it when it comes to direct impact. And one more chapter or sub-chapter we should cover is oblique impact. So before, these two black velocities, so these two black vectors, they were aligned with this line of impact. Yep. In oblique impact, these two velocities are not aligned with that line of impact. So what did we do on Wednesday? We just project it. Yes, we project this black vector on these two green directions, and this black vector on these two red directions. I don't know what I said earlier. Earlier I want to say green, now I want to say red. Okay. And if we do that projection, we have something for free. Yes? These components, these tangential components, we know even without calculating them. Yes? Because these guys must be equal to their counterparts pre-impact. This is exactly what I wrote in here. Yeah. So in other words, this green vector post-impact has to be equal to this green vector pre-impact. Yes, and this red vector post-impact has to be equal to its counterpart pre-impact. We have them for free. And now question to you guys: how to find these components, these normal components? Just repeat the procedure from the previous step. Yes, just apply our procedure from the direct impact, but this time only focus on the normal components of the velocity. We did it on Wednesday, I believe. Yes. That's all I want to say about oblique impact. And there's one more thing: angular momentum, that is not covered on midterm 2. Yeah, that would be my review. Thank you for listening. And the mic is yours. Just in case you have any questions, I can try to answer them right now. Anybody? Yes. Yeah. I think you did it in the lecture, yes? You probably did even more complicated problem in the lecture. Yeah. And I will also generate a PDF of that and I will send it to you. But thank you for writing it down. Yeah. Okay, guys, you have no questions. I have nothing else to say. By the way, did I make you more confused? No, it's good. It was good revision. Okay. So I will keep my fingers crossed for you on Monday. Good luck and see you soon.